Welcome to the deep dive. Today we're tackling something truly mind-bending, an idea that sounds straight out of science fiction. The assertion that we are living in a quantum simulation matrix confirmed.
It does sound wild, doesn't it?
Absolutely. But this isn't just philosophical musing anymore. It's being presented as a direct challenge to physics, suggesting we might need to ditch classical thinking entirely and accept reality as, well, as code.
That's right. The core idea, pulling together the threads from our sources, is that the universe's biggest puzzles, things like dark matter, unifying gravity, and quantum mechanics, might only make sense if we seriously consider this hypothesis, that reality is fundamentally information-based, an emergent program.
So the big question is, are classical physics, even general relativity, just approximations? Is gravity itself more like a feature of a cosmic operating system than some fundamental geometric force?
That's the paradigm shift being proposed. And the key, according to the synthesis of these ideas, is the quantum-unified vacuum theorem, which uses a tensor called Qμ-Modified. This is presented as the mathematical framework, the sort of source code for this emergent reality.
Qμ, okay.
Yeah, the Qμ theorem aims to provide that rigorous structure. It does this by integrating quantum information, specifically entanglement, right into the equations describing spacetime geometry. What emerges isn't a smooth, static background, but this dynamic, scale-dependent network of entanglement that acts remarkably like a high-fidelity quantum simulation.
Okay, so our mission for this deep dive is clear. We need to unpack this Qμ tensor, figure out what the components mean, understand how these derived constants like alpha and gamma supposedly dictate the laws of physics.
And crucially, look at the evidence.
Right. The multi-messenger tests from the scale of the entire cosmos down to lab experiments that could actually confirm or deny this whole simulation hypothesis. We're basically trying to reverse engineer reality's code.
Exactly. Let's dive in. So to start reverse engineering, you need the instruction set, right? The master equation. That means, going back to Einstein's famous field equations, the EFE.
Okay, the EFE. That's Gμ equals essentially Tμ. Geometry on one side, mass and energy on the other, tells matter how to move, matter tells space-time how to curve. The classic picture.
That's the classical picture, yes. Beautiful, but potentially incomplete if reality is computational. The Qμ framework modifies it. The equation becomes Gμ plus lambda Gμ equals 8pg over c to the fourth times, and here's the key bit, Tμ plus Qμ.
Whoa, hang on. So you're adding Qμ right next to Tμ, the stress-energy tensor for regular matter and energy.
Precisely.
You're saying quantum information, represented by this Qμ, contributes to the curvature of spacetime. It has gravitational weight.
That's the core assertion. Qμ is the stress-energy tensor of quantum information itself. It's the mechanism where the simulation's code, the structure and tension in the vacuum's entanglement network, directly influences the geometry. Information content dynamically interacts with energy content.
That's a huge conceptual leap. Gravity isn't just responding to mass and motion, but to data, to entanglement patterns. Okay, we definitely need to break down this Qμ tensor. You said it has three components, like three fundamental rules for the simulation.
We can think of them that way, yes. Three architectural parameters governing how information shapes geometry.
All right, let's take them one by one. Term one, the alpha term, curvature thermal coupling.
Okay, this term looks like alpha times Rₘ T minus 1/2 Gμ RT. The key things here are the curvature tensors Rₘ and R and this T representing local thermal energy.
So it directly links geometry, the curvature, to heat.
Exactly. The implication is pretty radical. Regions with intense curvature, think black hole event horizons. Or maybe the very early universe aren't just geometrically weird spots, they are inherently hot zones, thermodynamically active.
So the simulation sort of heats itself up based on how complex its geometry gets. Like, it's trying to maintain some kind of thermal balance with its own structure.
That's a great way to put it. It connects directly to ideas like Jacobson's, that gravity might be emergent thermodynamics. But here, it's baked right into the fundamental equation. The simulation makes geometric complexity pay an energy cost, linking the structure to the heat budget.
Okay, that paints a very dynamic picture. Let's move to term two, the beta term, entropy gradient stress. You mentioned this is like a control mechanism.
Yes, and potentially the mechanism that explains away dark matter. This term is beta times Kb times gradient mu s, gradient nu s minus 1/2 Gμ gradient S2. The critical part is that gradient of S, the gradient of entanglement entropy.
Gradient of S. So a change in entanglement entropy over space. That's like a measure of how disordered the quantum information is locally, right?
Precisely. And this term says that if you get a steep gradient, a sharp imbalance in local quantum information or disorder, it doesn't just sit there. It generates a stress, it pushes back on the geometry, it acts like gravity.
Like a program automatically smoothing out errors or complexity spikes?
Exactly like that.
Mm.
The theory posits that this entropic stress, this pushback from information gradients, is the force we currently attribute to dark matter in galaxies.
Right.
It's not missing matter, it's the universe reacting to its own quantum information structure. It looks just like an invisible gravitational pull.
Wow. Okay. And the third piece, term 3, the gamma term. Quantum fluctuation stress, the random element.
You got it. This is gamma times sigma mu sigma nu minus 1/2 g mu nu. Sigma alpha. Here, sigma mu represents the inherent quantum fluctuations, the fuzziness baked into quantum fields.
So this is the simulation's built-in noise, the source of quantum uncertainty.
Essentially, yes. It's the irreducible randomness. This term ensures that even the vacuum's geometry responds to this fundamental quantum jitter. It stops the simulation from being purely deterministic.
Okay, so we have heat coupled to curvature, stress from information disorder, and baseline quantum noise. It sounds like a reality constantly computing and adjusting itself. But physics hinges on conservation laws. Energy, momentum, they have to be conserved, right?
Absolutely critical. And this is presented as a major strength of the Qμ framework. The conservation law, nabla moralo mu b mu nu plus Qμ nu equals 0, meaning the total stress energy, matter energy plus information energy, is conserved locally. This isn't just assumed.
It's not.
No, it's mathematically proven within the framework. It falls directly out of combining the modified EFE with the Bianchi identity's fundamental geometric rules that curvature must always obey. The conservation, specifically nabla mu Qμ nu equals 0, is a mathematical necessity for the whole thing to be consistent. The simulation's code conserves energy and momentum.
All right, we have this mathematical code, Qμ nu. But how does code on paper become the physical space and time we actually experience? This is where the it from qubit idea comes in, I gather.
It is. The engine driving this emergence is understood through holographic duality, particularly inspired by the AD-SCFT correspondence.
AD-SCFT, anti-de Sitter space conformal field theory. The idea that gravity in a higher dimensional space, the bulk, is equivalent to a quantum theory without gravity on its lower dimensional boundary.
Exactly. Qμ nu theory leans heavily on that principle. Our 3D reality, plus time, the bulk, emerges from the information encoded on a kind of lower dimensional boundary, the information layer.
And the bridge between that boundary information and our bulk reality is the Ryu-Takayanagi formula.
That's the crucial connector. Ryu-Takayanagi gives us a way to calculate entanglement entropy, that S in the beta term, within our gravitational bulk. How? By measuring the area of the specific minimal surface on that lower dimensional holographic boundary.
Okay, that's pretty mind-bending. So the entropy S in the Qμ nu term isn't just some abstract number. It corresponds to a real geometric area on this boundary screen.
Precisely. Space-time geometry literally emerges from the pattern and density of entanglement connections. When you measure distance or curvature, you're effectively probing the complexity of this underlying entanglement network. The universe isn't just described by physics. It is a vast quantum computation where the connections themselves define the space.
This sounds like a continuous process, then. The simulation constantly turning quantum information into the classical world we see, the quantum to classical bridge. Does this tie into the quantum measurement problem?
It absolutely does. The framework draws on Zurek's work on decoherence. You know how quantum systems lose their quantumness, superposition, entanglement when they interact with their environment.
Right, they sort of collapse into a definite state.
Well, Qμ nu theory suggests this is happening constantly. The Qμ nu tensor itself embodies the quantum weirdness, but the interaction and the resulting decoherence, driven perhaps by the entropy gradients in the beta term, are what make things appear classical to us, described by Qμ nu.
And the sources use this interesting analogy, the quantum Hawking radiation analogy. How does that fit?
It's a way to visualize the creation of space-time itself. Think of the pre-geometric state as maybe a purely 2D time-light field on the boundary. The analogy suggests the transition from that 2D information layer to our familiar 3D reality is like Hawking radiation emerging from a black hole horizon.
So interactions or collisions in that 2D layer create a kind of pre-geometric horizon.
That's the idea. And at that horizon, entanglement fluctuations may be linked to the gamma term's noise, decohere rapidly, condensing into the 3D space-time quanta we perceive. It's like reality is constantly radiating into existence from an information boundary.
Which implies there's thermal energy involved in this emergence, bringing us back to the Unruh effect and the alpha term again.
Exactly, it all ties together. The Unruh effect is the direct physical manifestation of the alpha term. Remember, Unruh predicted that if you accelerate through a vacuum, you perceive a thermal bath, a temperature Tu proportional to your acceleration A.
Heat generated just by accelerating?
Right. And the Qμ theory says this local temperature, T, which is linked to the Unruh temperature, is coupled directly to spacetime curvature via that alpha term and something called the discrete entanglement, Hamiltonian, He.
So when geometry curves, which is equivalent to gravity or local acceleration, it must generate thermal energy according to this theory.
Yes. The Unruh temperature becomes a direct readout of the simulation's internal thermal coupling, dictated by alpha. It's the simulation paying the energy price for creating local structure and acceleration. Okay, so if this is a unified code running the universe, then the fundamental constants, things like the strength of electromagnetism, shouldn't just be arbitrary numbers someone dialed in. These should be necessary consequences of the simulation structure.
They have to emerge from the code itself.
Exactly. And a structure proposed in these sources is deeply tied to fractal geometry.
The fractal holographic principle. The idea that reality structure looks similar at different scales, maybe across orders of magnitude, like $10 dolls, and that quantum mutual information is preserved across these scales.
That's the concept. A common code repeating itself, creating self-similar structures.
Yeah.
And if the vacuum is fractal, it has a specific fractal dimension, df, which isn't necessarily an integer like our usual three spatial dimensions.
And this fractal dimension is supposedly the key to deriving fundamental constants, like the fine structure constant, alpha EM. That seems incredibly ambitious.
It is audacious, absolutely. The claim is that the gamma constant in Qμ, the one governing quantum noise, is actually derived from both the fine structure constant, alpha EM, roughly 1137, and this underlying fractal dimension df.
And they have a specific value for this dimension.
The sources point to df's frac log 8 log, which is approximately 1.8928. This is the dimension associated with structures like the Sierpinski gasket or triangle shapes known for maximizing boundary or surface within a given space. Very efficient packing.
Okay, so the simulations-based geometry might be this fractal structure. But how does that number, 1.8928, dictate the strength of electromagnetism, 1137?
The argument is based on information conservation. To maintain consistent quantum mutual information, the computational link between points across all scales in a vacuum structured with this specific fractal dimension, the coupling strength of the electromagnetic force must take the value we observe for alpha EM.
So 1137 isn't random. It's a requirement for the simulation's fractal code to run consistently. The way light interacts is basically a property of the dimensionality.
That's the implication. It reframes alpha EM from a mysterious measured value to a geometric necessity.
Mind-blowing if true. Okay, what about the other big constant, the alpha from the first Qμ term? The energy coupling constant. Its value is enormous, right?
Huge. Roughly $1.72 times 10 suppleants in standard SI units related to temperature squared. The reason it's so large comes from applying statistical mechanics concepts to black hole thermodynamics within this framework. You essentially model the black hole's geometry like a thermal system.
And this huge number, alpha, what does it do? What's its role in the simulation?
It sets the exchange rate between classical mass energy, Tμ, and the stress from quantum information, Qμ. It dictates how sensitive the geometry is to the entanglement structure.
So if alpha were smaller, gravity would be less affected by these quantum information effects.
Precisely. Its immense size means that while Qμ effects are subtle normally, they become overwhelmingly dominant where curvature is extreme near the Planck-scale, inside black holes. It's like the simulation cranks up the resolution or the importance of the quantum code in those regimes.
But wait, if these constants are derived, are they fixed? You also mentioned a dynamic code earlier, the scale-dependent coupling alpha k xi.
Ah, yes, that's crucial for making the theory work across cosmic history. The physics isn't static. This function, alpha kz equal Alivero divided by 1 plus k star 2, where k star depends on redshift z, shows the coupling strength isn't constant.
Okay, so alpha changes depending on k, the scale you're looking at, like small quantum scales versus large cosmic scales, and z, the redshift, which tells you the epoch of the universe.
Exactly. This running coupling is vital. Why? Because at very large scales, low k, like galaxies and clusters today, the denominator gets big, making the Qμ correction term effectively disappear. So the theory naturally recovers standard general relativity where we know it works well. That's a critical consistency check.
But at small scales, high K.
At high K, or potentially very early times, high Z, the coupling alpha becomes strong. The Qμ term dominates. This scale dependence essentially acts like an inbuilt energy cutoff or regulator. It might suggest the simulation has finite resources, and it handles things differently at its fundamental resolution limit.
Theory is elegant, but does it match reality? The Qμ hypothesis has to make predictions we can actually test, problems it can solve. Let's start with cosmology's biggest headache right now, the Hubble tension.
Right, the Hubble tension. The fact that measurements of the universe's expansion rate today, from things like supernovae or the DESI survey, give a different value for He0 than measurements based on the early universe, like the Planck satellite data. It's a major crack in the standard cosmological model.
How does Qμ, with its scale-dependent coupling alpha K, fix this?
The core idea is that gravity's effective strength isn't constant across cosmic time and scale, precisely because of alpha kz. The Qμ framework predicts that the entanglement correction slightly suppresses the growth of large-scale structures later in cosmic history. It effectively makes gravity a tiny bit weaker on certain large scales, particularly those probed by techniques like baryon acoustic oscillations, BAO.
BAO, those cosmic sound waves used as standard rulers, if gravity was slightly weaker when those structures formed.
Then to match the BAO observations today, the universe would have had to expand slightly faster in the recent past. This modification to the late-time expansion history, driven by the scale-dependent coupling, leads the Qμ framework to predict a late-time Hubble constant, around 68.2 km/MPC.
And that matches?
That aligns very nicely with the late-time measurements from DAR and similar surveys. So it resolves the tension by saying Hz0 isn't fundamentally constant across all measurement techniques, because gravity itself evolves subtly due to the Qμ term. The simulation dynamically adjusts its parameters.
Okay, that's a potentially huge win. What about the other big mystery, dark matter? You mentioned the beta term, the entropic force replaces it.
That's the proposal, the entropic force solution. When you apply that beta term, the stress, from entropy gradients to the scale of galaxies, it naturally generates an extra acceleration. This acceleration mimics exactly the effect we currently attribute to unseen cold dark matter, CDM, in explaining why galaxies rotate faster than expected.
So, no need for exotic particles. The missing gravity is just the space-time reacting to its own information structure.
That's the argument. It's the resistance of the vacuum to entanglement disorder manifesting as an attractive force.
And this isn't just hand-waving. There are specific predictions. You mentioned spark data.
Yes, it makes a direct, falsifiable prediction. The model naturally recovers the baryonic-Tully-Fisher relation, or BTFR. That relation empirically links a galaxy's rotation speed, Vrot, directly to its baryonic mass, OMB. The mass we can actually see specifically, Vrot to the fourth power, is proportional to MB.
So the rotation is tied only to the visible matter and the local entropy gradient.
Exactly. It's a natural outcome if Qμ dominates over standard gravity at those large galactic scales where accelerations are low. It predicts the BTFR without needing any dark matter fudge factor, and this can be tested against detailed galactic surveys like SPARC.
Okay, moving from galaxies to the most extreme gravity, black holes. What does Qμ predict for them, especially when they merge, like in gravitational wave events? You mentioned GW250113.
The key prediction is no singularities. In standard GR, a black hole collapses to an infinitely dense point. But in the Qμ simulation, as matter gets crushed towards Planck density, the entanglement correction terms become strongly repulsive. They fight back against the collapse.
Like a quantum pressure preventing infinite density?
Sort of, yes. An entropic pressure or stress. It acts like a firewall, preventing the singularity. So black holes can't collapse completely. They must stabilize into a tiny, dense, quantum-structured remnant.
A leftover core? How big?
The theory predicts its mass is directly linked to that fractal dimension, dF. The remnant mass should be m Planck divided by the square root of dF, which works out to about 0.726 times the Planck mass. It's a stable core structured by the simulation's fractal geometry.
Fascinating. And how could we possibly observe such a thing?
Through gravitational waves. When black holes merge, they ring down, emitting waves as the final object settles. Standard GR predicts specific ring-down frequencies based on the final black hole's mass and spin, the Kerr solution. But if there's a stable fractal remnant inside, it would vibrate differently, like a tiny complex structure. This should add extra unique, higher frequency modes to the ring-down signal, beyond what standard GR predicts. Finding those specific extra frequencies in a high-quality signal like GW250114 would be the smoking gun evidence for this remnant structure and the Qμ effects in strong gravity.
Amazing. Okay, let's bring this down to the lab. Can we test Qμ on Earth? You mentioned the LUXE experiment and quantum interferometry.
Yes, these offer potential terrestrial tests. LUXE aims to measure the Unruh effect, that heat bath seen by accelerating observers, by using intense lasers and high-energy electrons to create extreme accelerations.
How does Qμ change the prediction?
It predicts the Unruh signal should be enhanced, because the alpha term directly couples the thermal field Unruh radiation to the local curvature acceleration. The signal should be stronger than baseline predictions. Specifically, the sources suggest looking for an Unruh-Compton scattering ratio greater than 10 or 3.
So it's not just detecting Unruh radiation, but detecting more of it than expected by a specific amount.
Exactly. And the spectrum of the detected radiation, its energy distribution, must precisely match the temperature predicted by the theory based on the acceleration, that Tx formula. Tx equals h bar over 2 pi CKB times the square root of the relevant curvature component. It's a direct probe of the alpha term in action.
And the beta term, the entropy gradient part, how do we test that in a lab?
Through high-precision quantum interferometry. You split a quantum particle's path, let the paths evolve differently, and then recombine them to see interference patterns. Qμ predicts an anomalous phase shift in these experiments. The total phase shift, delta phi, would be the standard quantum mechanics shift plus an extra term, etas times gm squared over h bar c times alpha times delta s.
Let me unpack that. Delta S is the difference in entanglement entropy accumulated along the two paths.
Correct.
And that difference in entanglement via the alpha coupling constant actually changes the particle's phase. It changes the effective geometry the particle experiences.
That's exactly the prediction. It would demonstrate that a difference in the local quantum informational state, the entanglement structure, directly produces a gravitational effect, a change in space-time experienced by the particle. It's a direct test of whether entanglement stress sources gravity, just like the beta term in Qμ says it should. #tag outro.
So we started this deep dive with what seemed like a sci-fi premise, living in a quantum simulation. But by synthesizing the ideas around the Qμ framework, we've seen how it aims to provide a potentially testable mathematical basis for that premise.
Right. It's moved beyond just philosophy.
We saw how it modifies gravity to include information, potentially resolving the Hubble tension by making gravity dynamic, replacing dark matter with entropic stress.
And making concrete predictions for black hole physics and even lab experiments. It weaves together gravity, quantum entanglement, and fractal math into one story.
It really does try to build a cohesive picture.
And perhaps the most profound shift in perspective, if this holds up, is how it deals with quantum weirdness, like entanglement. That spooky action at a distance Einstein worried about.
Yeah.
It's reframed. Instead of spooky action across distance, Qμ suggests it's more like geometrical connection without fundamental distance. Those non-local correlations aren't bugs in spacetime. They are the very threads creating spacetime. They define the geometry.
Wow. Locality itself becomes an emergent property of the connections, a total rewrite. So if the universe is this simulation running on the Qμ code, what's the big unanswered question within this framework?
Well, one crucial piece is still undetermined. The precise value of that beta constant, the one linking entropy gradients to stress energy.
Why is that one so important?
Because entropy S is fundamentally about information. Nailing down beta would essentially tell us the computational efficiency of the simulation, how much gravitational cost is associated with managing information and disorder. It might reveal the resource limits of this cosmic program.
Resource limits. What happens if the simulation starts hitting those limits? Could the code break down?
That's the final provocative thought, isn't it? What kind of new physics, maybe even geometric instabilities, could emerge if the universe's computation starts to strain? What does that imply for the future, for the very stability of reality as we know it? That's the next frontier this kind of thinking pushes us towards.